Good morning, everyone. My artificial neural networks topic is about unsupervised learning with autoencoders. Autoencoders are powerful neural networks designed for unsupervised representation learning. They excel at discovering efficient data coding without the need for labeled data, making them a key tool for tasks like dimensionality detection and feature extraction. What is autoencoder? First one is we need to know about encoder to know about autoencoder. Encoder is nothing but the process of compressing input data into a lower dimensionality Latin code, and it captures the only the essential features. The second one is latent space, which is a bottleneck, a compressed meaningful representation of the input that forces the network to learn efficient encoding. And the third one is decoder, reconstructs the original input from the compressed latent code. First step, whatever the given data, that data it captures the essential features, and from that essential features are converted into lower dimensionality latent code. It removes the inconsistency, it removes the unnecessary features, it removes the redundancy in the data, and the noise free data is compressed into a lower dimensionality latent. And the second one is a compressed meaningful representation of the input. These forces the network to learn efficient encoding. And the third one is decoder. It reconstructs the original input from the compressed latent code. And the second step is latent space, which is also known as bottleneck. In this, uh, whatever the compressed dimensionality Latin code is there, it gives the meaning to that Latin code by easily understandable, by uh, representation of the data in an easily understandable way, and for the efficient encoding, and gives the meaningful input to the input data of the lower dimensional Latin code. And third one is decoder. It reconstructs the original input from the compressed Latin code. The primary goal of a latent encoder is to ensure the output closely approximates the original input, maximize the reconstructions error. The training encoders. The network minimize reconstruction error, often using mean square error, which is also known as MSE. Input data serves as its own target output, making the process unsupervised. Backpropagation is used to optimize network weights, gradually reducing the loss. Architectural constraints prevents the network from simply copying the input, forcing it to learn meaningful expectations. Input data serves as its own target output, making the process unsupervised. Backpropagation is used to optimize network weights, gradually reducing the loss. Architectural constraints prevents the network from simply copying the input, forcing it to learn meaningful representations. The network minimized construction error, often use mean square error. The self-supervised learning approaches allows encoders to find hidden patterns in data without any human provided labels. In this process of auto encoding, it only finds the hidden patterns without the involvement of the human. It only deals with this unsupervised machines to train this. Next one is bottleneck and dimensionality reduction. As we have learned earlier, the three steps, which is encoder, and the second one is uh, bottleneck, and the third one is decoder. In the first step, information constant, the from the input data, the only the essential features are extracted, and from that features it compresses into the input data of the decomposition Latin code, and it makes sense to the bottleneck, where it gives the meaningful features to that Latin dimensionality Latin code. And in the third decoder, it comprehends the representation, whatever the data, whatever the representation of the dimensionality Latin code, it represents in the kind of format from where the essential features are extracted typed. Uh, as we can say that the output achieved by this decoder is same of the input format of the extracted essential features. The bottleneck layer is designed to limit information flow, forcing the autoencoders to learn a compressed yet meaningful representation of the input code. That makes autoencoders a powerful non-linear generalization of PCA capable of learning complex data manifolds. For instance, a 100 pixel image input might be compressed into just 500 hidden units in the bottleneck layer. As we can also say that the bottleneck is mainly used for the dimensionality reduction, whereas we can say that suppose it consists a 160 into 160 pixel of image. That 160 pixel of image can be reduced into 2 into 2 pixel without disturbing the format, without making the image blur, or without disturbing the features of the image. So we can also say that there will be no data losses, there will be no noise construction blur of the image. And bottleneck is very useful for just to compress, not only for the compression, for the dimensionality reduction of any kind of data. Second one, next is exploring auto coder variants. There are 4 types of autocoder variants. One is undercomplete, second one is sparse, third one is denoising, and the fourth one is contractive. Whereas coming to autoencoder variants, these are beyond the basic architecture. Several specialized encoder types have been developed, and each addressing specific challenges or enhancing learning capabilities. Undercomplete, fewer hidden units than input dimensions, forcing direct dimensionality reduction. Impose sparsity constraints on hidden layer activations, encouraging distant feature learning. And denoising, it reconciles clean data from corrupted or noisy input, enhancing the robustness. Contractive, it adds robustness by penalizing sensitivity to input perturbations, promoting stable feature extractions. Third one is sparsity and regularization. Sparsity is in autoencoders is mainly used for the neurons in the hidden layers to remain inactive. Their activation value are nearly zero or less than the zero. This is achieved by adding specific penalty terms such as KL divergence to loss function. This technique is crucial for preventing overfitting to the training data. Next, encouraging the network to discover distance and useful features, balancing reconstructions accuracy with model generalization. Variation autoencoders, which is also known as VAEs. Unlike traditional autoencoders, VAEs are probabilistic models that map inputs to latent distributions rather than discrete points, not the continuous points but to the discrete points. This unique approach allows to generate capabilities, whereas the key features of this variational autoencoders are that the encoder outputs parameter, which is known as mean and variance of a latent distribution. And second key main feature is that the decoder samples from the learned latent space to reconstruct the input. VAEs are excellent for generating new similar data points and for semi-supervised learning tasks. Autocondensive reconfidence and autocondensive reconfidence. Practical applications of these autoencoders are that autoencoders find diverse applications whereas across different domains, leveraging the ability to learn efficient data and representation. First one is dimensionality reduction, simplifying complex datasets for visualization and more efficient pre-processing in machine learning workflows. Second one is anomaly detection, identify the outliers or abnormal data points by analyzing high reconstructions errors. And the third one is feature extractions, deriving robust and compact features for improved performance in classification and clustering tasks. Next one is data renoising and reconstruction, restoring original data from noisy inputs, particularly effective in image. Advantages and limitations of these autoencoders. Advantages are that unsupervised learning learns from unlabeled data, reducing the need for costly manual annotation. Non-linear feature learning, capable of discovering complex non-linear relationships in data that linear methods might miss. Flexible architectures can be adapted for various data types and tasks by modifying network layers and configurations. And the limitations is the risk of overfitting. If not properly regularized, they can learn to simply copy the input, failing to extract meaningful features. Information loss, the compression process may inadvertently discard vital information, impacting reconstruction quality or downstream tasks. Hyperparameter sensitivity. Performance heavily relies on parameters like bottleneck size and regularization strength, requiring careful tuning. Not always ideal, may not be the best choice when a rich label data or express supervised learning goals are present. Summary is that unsupervised learning and it has feature extraction and versatile variants and broad applications. Embrace autoencoders to uncover hidden structures and enhance data utility in your machine learning pipeline. Thank you.